We have to prove here that this is a set of rational numbers, excluding -1, is an abelian group with this operation. Well, the first thing we need to check is whether this operation produces, given any two rational numbers other than -1, produces also a rational number which is not -1. Well, obviously, the product and sum of rational numbers is a rational number, so the only condition that we need to fulfill is that this is not equal to -1. So let's see what is the condition for this to be equal to -1. That would be, if that happens, then the operation is not closed in this set. So if we put this one here, what we have is this. This xy equal to 0, right? Which can also be written as 1 plus x times 1 plus y, right? You get 1 times 1 is 1, and then you have x, then you have y, and x times y, and that is equal to 0. But for this to be true, either this has to be 0 or this has to be 0. In other words, either x is equal to -1 or y is equal to -1, but neither of them can be equal to -1 because they belong to this set here, so this is never 0. So since this is never 0, this is never -1, and then this is a valid operation because this product belongs to G, no matter what x and y are, if they are elements of G. Okay, that's the first thing. So now we need to check the properties of of the group. So the first one is associativity. So what we have to do is to make this operation and then do the operation with the third element, which is not -1. So the operation with this is equal to this one, so it's x plus y plus x times y times z, right? And the operation of this is, well, the first thing is, when you have to operate two numbers, the first thing is to add them up. So you have to add this and this, so it's x plus y plus xy plus z, right? And then the second thing is that you have to multiply them. So you have x plus y plus xy times z, right? And if we expand this and order it a little bit, you have x plus y plus z, right? So these two and this. Then you have here xy. Okay, you have xz, and then you have yz. And finally, you have xyz. And now in principle, we should do the same operation, but this time in this way, okay? Y times z. There's no need to do this because, as you can see here, this operation is symmetric under any interchange of these x, y, and z. So you make any interchange of variables, and then you get exactly the same result because this is symmetric under those interchanges. So this has to be equal to x times y times z, right? And not only that, you can check because of the symmetry of this expression. I mean, you can change x and y here, and then you will get the same operation here, the same result, that this is also commutative. So this is associative, and commutative. All right, you have these two. Now let's see what happens about the neutral element, right? That's G2, okay. The neutral element is, well, let me just copy what this product is. This is x plus y plus xy, okay. And what we need here is a y such that this is equal to x, right? So it's clear that y has to be 0 for that. Because if y is equal to 0, then this is just equal to x. So this is the neutral. Right? That's the neutral. Okay. And finally, let's see if there's an inverse. For an inverse, what we're looking for is a y such that this operation gives you 0, because 0 is the neutral, all right? Okay, so we're looking for y. So here we have x plus, and then factor out y, and you have this equal to 0. So you put x on the other side, you have 1 plus x times y equal to negative x. And since this is not 0 because all the elements of the set are different from negative 1, then y is negative x over 1 plus x. So that's the inverse of every number x with respect to this product. So you see, this is a non-abelian, it's an abelian group, okay, with respect to this operation.